Alright, so last time we had actually talked about one of our problem-solving strategies. We generally talked about several of them, but the one that we had actually taken a look at was a problem-solving strategy about patterns. It was a particular problem set by a mathematician named Gauss when he was quite young. And he found a way basically to add a bunch of numbers together in a much faster way. That's sort of what we did. And we're going to take a look at a problem that is similar to this, and the strategy that we're going to be using is to examine a related problem. And that should sort of make sense, because if you take a look, what we've got is a bunch of numbers that we're adding together, and we'd like to do it in a more efficient way than literally adding them together, which sounds a lot like what Gauss did. But the numbers aren't 1 to 100, which means that we have a different sort of a ratio going on. Is everybody with me? Okay. So it would be helpful perhaps to take a look and figure out if we paired the numbers up, that was what Gauss did, what kind of a pairing do we get? So we're going to pair up these two and these two. What is 36 plus 147? You should calculate out. Somebody said, tell me. 183. 183. And what is 37 plus 146? 183. So all of my sums are going to be 183 on this one. Instead of like when Gauss did it, they were, I think it was 101, wasn't it? Okay. So what Gauss did next was, or what we did last problem on Gauss's problem, was to say S equals, that is my sum equals, and we replace every single number with the number's sum, which, and its pairing, which will be the number 183. So I'm going to have a whole bunch of 183s added together. But the reality, of course, is that that's real. Oh, why did I put 182 in the last one? That's interesting, isn't it? The reality is that's too much. How much too much? Twice, because I replaced every number with the sum instead of just half of the numbers with the sum. So this is twice as many as it was before. Has it finished going around? Might be done. Yeah. Did everybody sign in on the sheet? They did get that correction. Okay. All right. This is two times as much as we really need. What did we do next? Remember? Right, so what this really is, it's 183 added together a bunch of times. We need to figure out how many times. And the number of times is the number of numbers we were adding. So we started at 36, and we went up to 147. Everybody good with that? Let's suppose for a moment, instead of starting at 36, we really just started with the number 1. If we went from 1 to 147, how many numbers would we have? 147, right? But we don't really have 147 because we don't have the numbers from 1 up to 35. How many numbers are there from 1 to 35? 35 numbers. So I had 147 numbers and I want to remove the first 35. That sounds like subtraction, right? So if I took 147 and I remove the first 35 numbers, what do I get? 112. There are 112 values I'm adding. Now what? There's a couple different things we can do.
Either divide by 2 or
The two things. So we can either divide the two to the other side, or we can multiply those two numbers together. Which one do you want to do? Multiply. Okay, so somebody tell me what 183 times 112 is.
2,496.
Good. Then what? Then we're going to divide by 2. And what do you get? 10,200 and what? 48. And that's what we were looking for. Is that okay? So we we took that strategy that Gauss used and we sort of applied it more broadly.
Strategy number 3, or example number 3, another strategy. The strategy we're going to use on this one is to examine a simpler case. And here's what it says. If a soccer league has 10 teams, and each team plays every other team once, how many total games are played? So we're going to simplify the situation until we can figure out how we can make that determination. Okay? So one thing legitimately we could do is we could give all the teams a letter or a number or something like that and draw pairings. We could do that, right? Sounds like it would take a while to me. I don't like, not with 10 teams anyway. I don't like that responsibility with 10 teams. We just had 4 teams, maybe. That's fine. 10 teams? I don't know. So what we're going to do is we're going to consider a smaller case. Let's consider 3 teams. Let's call them Team 1, Team 2, and Team 3. So how many games will Team 1 play? 2 games, right? Team 1 plays 2 games. How many games will Team 2 play? 2 games. And how many games will Team 3 play? 2 games. So there's 6 games total. Or is there? No, there are not 6 games total. Why not? Every game was counted twice. I counted it when I counted Team 1, and I counted it when I counted Team 3, for your example, right? Every game I counted 2 times. So what I really need to do is I need to take the number 6 that I got at the end and do what with it? Divide by 2. So there's really a total of 3 games played. All right, so let's go through what we just did. We took the number of teams, which was 3, times how many games each of them would play, which would be 2, and it's 2 because it's 1 less than the number of teams, right? And then what we did is we divided the number by 2 for the double counting. Okay, so this is my number of teams. This is my games per team. And then the 2 removes double counts. All right, so let's extend this idea back up to 10 teams. So if I have 10 teams, how many games will each team play? 9. So I've got 10 teams playing 9 games each, but if I just do 10 times 9, I've double counted everything. So what do I need to do? Divide by 2. What is 10 times 9 divided by 2? 45. So there are 45 total games. And this is legitimately what you would have to do in this situation, right? Because you need an umpire or a referee or a whatever you call them with soccer, I don't know. Whatever you call them, you need one of those for every game, correct? You need to know how much money that you need to pay them to figure out how many games they're going to, get me refereeing for and all of that kind of thing. You need to know how many games that you need to cover, because this is what you'll be looking for. And how many maybe fields you have to work with and things like that for timing. Okay, let's try another strategy. So the strategy we're going to use on this one is going to be to make a diagram. I'm not an artist, so my diagram's going to be terrible. Right? I promise you that. Here's the description. It says, a store sells bicycles and tricycles.
There are a total of 15 cycles, modes of operation, if you will, in the store, and there are a total of 35 wheels on those 15 cycles. The question is how many types of each cycle are still sold in the store. And while you could do this with equations, right? You could do this with equations, that's a legitimate way to do that. Probably the children that you would be working with wouldn't do that with the equation, right? That kind of equations and solving is typically a high school topic. It's not something you would use at this level, but they can do this problem. And you can too at their level. So think about it from this perspective. I know I have 15 cycles, right? And they have how many tires at least? 2. So I'm going to draw, that's my cycle, it has 2 wheels. Are you with me? We're going to draw 15 of these guys. All right, I just used a button. I didn't tell you I did it. Did I do this last time in this class? I don't think I did. Did I do the infinite cloner last time? Did I? In here? I know you've seen it before. But did I do it in this classroom last time? Okay. All right, so what I did is I actually highlighted everything I had. I want to show you the things I'm doing on the smartboard so you'll know some of the cool things it does. And I selected a button, so. All right, I said I did it. I'm not going to let me do it again. These are the ones I'll show you again on the screen. And I selected a button in the drop-down menu that said Infinite Cloner. What the Infinite Cloner is going to allow me to do, did it only pick up that one too? Well, we'll see. What the Infinite Cloner is going to allow me to do is to copy it multiple times. So you put your hand on it and you drag it down and you get an instant image that you just had before. So I don't have to draw 15 of these. In theory, I should have only had to draw 5 the way I did it, but I screwed up. So we'll draw another one over here. You have to draw a bunch of things, and you probably would be doing it prior to actually in class with your students. That'd be a handy feature. And you don't have to have a smartboard either, as long as you have your computer, your mouse will do it too. So you can create images like that with your computer for a test meeting or a handout that you want to do for your students, which is pretty handy. All right, so I have 15 of these. How many tires or wheels or whatever do I have? There's 30. How many am I supposed to have? 35, which means what do I need to do? I need to add some wheels to what I've got to make them tricycles. How many do I need to turn into tricycles? 5. So we're going to pick our favorite 5, and we're going to add a third wheel to each of them somewhere on there. I don't care where you put them, but you're going to add a wheel. Now your image actually fits the description that's given. You have 15 cycles. That's how we started. And 5 of them we turned into tricycles. The other 10 we left as bicycles. Be careful to make sure you answer the question that was asked. The question said, how many of each type are in the store? So how many bikes do I have? 10. And how many trikes do I have? 5. And that answers the question. The next one, you guys didn't like this approach when I mentioned it last time, so we'll see if you like it any better with doing one. The approach is guess and check. You guys need feedback, it's very negative on this side. So, this one says, we have 48 feet of fencing and we wish to make an enclosure along one side of an existing barn. What length would the side need to be in order to have the greatest area enclosed? Again, can you do this in equations? Sure, that's an algebra topic, high school stuff. So that's not how we're going to approach this problem. We're going to approach this problem with guess and check. Now, thinking about the guess and check, I'm actually going to draw a picture to go along with the guess and check that describes what's happening so we make sure when we're doing the problem mathematically that we're processing it the right way. So we have an existing barn. So here's my barn. And we're going to use the side of the barn as one side of my fence. That's what it described. And it says the fence along the barn then has a certain area, oh, I'm sorry, has a certain length. We want the area to be as big as possible. My goal is to have a big area in here. What I do know is that this piece and this piece and this piece are the side of the fences, and they have to add up to 48. All right, so we're going to guess and check, but we're going to do it in as organized a way as we can. So we are going to figure out what do we want to let our lengthen or our width or whatever be. So we've got this piece and this piece that match. So whatever those are, they're equivalent. Okay? And then we've got the third side that may or may not be different. It could be the same number, but it would have to be. So somebody give me a side length for the green side that we might want to try. Number for me? 10. Okay. So if the green sides are both 10, what would my red side be? 28, right? All right, so this is the check part, and you don't know immediately on this one if your check gives you what you're looking for until you try something else. All right, so my guess is that it's 10, 10, and 28. And then how would I find the area with those numbers? Times what? What would be times? What is it?
Oh, one side by the other.
Okay, so, but I have three sides listed, so which two sides do you want? 10 and 28. So the image I have right here, right now, is that this is 10 and this is 28, right? So area is found for a rectangle by doing length times width. So the width, my top piece in green is 10, the side piece is 28. So the check for the area here would be 10 times 28, which would be how much? 280. Now we don't know if that's the largest, but it is an option at this point, right? So let's try something else. Our goal is to see if we can get a bigger number. 20 on the top and bottom. Okay. So we're going to do 20 and 20, which would mean the third side is, what is it? 8. All right, so let's check the area. What would I multiply for my area? 20 times 8, which would give me 160. So far, the first one's better. Now what? So we still don't use the S, though. What's that?
Two sides, 5.
Okay. So maybe we did 5 and 5 and what? 38. So my area would be found by doing what? 5 times 38. What's 5 times 38? What is it? 190. So far that 10, 10, 28 is looking pretty good. We've sort of deviated from the 10, 10, 28 by quite a bit when I've gone to 20 and then even down to 5. Can we try something a little closer to the 10, 10, 28 to see if we can get maybe a little bit higher or a little bit lower and see if we're on the right track? Like maybe, okay, let's try 12. So it'd be 12, 12, and what? What was it? 24? Okay. So my area would be then 12 times 24. And what is 12 times 24? 288. So I've got a new winner at the moment. 288 is bigger than 280. Okay. But it still may be that it could be better. How will I check? 13. Okay, let's give 13 a try. Because see, when I went from 10 up to 12, it got bigger. But if we go all the way up to 20, it's too big, right? Because that ends up giving me a smaller area. So maybe if I go up just a little bit more, we can see whether or not that gave me what I was looking for. So 13, 13, and what? 22. So
my area would then be 13 times 22, which is 286. So if I went just 1 foot bigger on the top and the bottom, the area became smaller. Right? There's really only one other thing to try, just in case. 11. Because it could be that when I went from 10 to 12, I skipped over the biggest area. That's a possibility, right? We don't know for sure, because clearly when I went from 12 to 13, the area went down a little bit. So let's try 11. 11, 11, and what? 6. What? 26, sorry. 26, that's not better. So my area being 11 times 26, which would give me 286. Do we have a winner? Yes. What's our winner, or who's our winner? 12. All right, so there's 2 questions that we need to be answering. It said, what lengths would the size need to be to have the greatest area enclosed? So it doesn't actually ask me for the 288, right? It asks me for the lengths of the sides. So we need to answer the question that was asked. The lengths need to be 12 what? Feet. 12 feet. Be consistent since I already wrote the first one out. And 24 feet. This isn't guess and check in the sense that it's random, right? You made an educated guess, you started somewhere, and then you tried to figure out whether or not that was a good guess by going higher or lower and looking at your result. So you're guessing, and then you're checking the result that you got to figure out if it was a good guess. Does that make sense? All right. Let's see what we have next. Working backwards. A favorite among many. Working backwards. So let's take a look at this particular one, because working backwards is a really good strategy. Example 6. One winter night, the temperature fell by 15 degrees between midnight and 5. By 9 a.m., the temperature had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. What was the temperature at midnight? So they're sort of telling you from midnight till, what was the last temperature we got? Noon. From midnight to noon, it made all these changes. And at noon, we know that the temperature is 32. So what was it back at midnight? You agree with me? All right, so let's see what we have. Well, we know that where we end up is 32 degrees. And that's at noon, right? What is the time just before noon that we have information about? 5 a.m.? 9 a.m., right? 9 a.m. actually. So 9 a.m. What's the time before 9 a.m. though, Haley? That one's your 5 a.m. And what's the time mentioned before 5 a.m.? Midnight, right? Okay. So at noon it was 32 degrees, and it says by noon, going backwards in the descriptors, right? It says it was 32 degrees. By noon it had risen another 10 degrees. So what does that mean the temperature was at 9 a.m.? It was 22 degrees. And it was 22 degrees because, oops, because from here to here, we know it went up 10. Now this is really bad lingo, but it's from your book, so you can suffice it. But the idea of temperatures doubling is just terrible. Those of you who have some sort of scientists should just cringe at this, because the universe temperature double. I mean, which scale are we on, and how are we looking at doubling? It's just not good. But let's just do it for the face value of what it's saying in that lingo, okay? So ignore the real physical implications, because it's not good. But you bear with me. All right, so it says though it had doubled from 5 a.m. to 9 a.m. We don't get too technical with what that meant. What was it at 5 a.m.? It was 11. Because this is supposed to be multiplied by 2, in essence. All right, and then one more thing is it says between midnight and 5 a.m. it fell by 15 degrees. So what is that going to tell me? Lots of
26 sounds good. So it's supposed to be 26 degrees here. Because from here to here, it's supposed to fall. That is, it's supposed to decrease from midnight to 5 a.m. by 15. So the opposite then to get up one more level would then to increase it by 15 to figure out what that was. So what was the temperature at midnight? It was 26 degrees. And also that's not good. We should be using some sort of scale. Evidently it should be Fahrenheit, so it will make sense, right? But it doesn't actually say that. So we're just going to leave it with 26 degrees. Okay, I want to show you one other thing before we leave. And the reason I want to show you this is because now we literally have to walk out the door and leave it before I turn the screen on. Okay, so is that you will need this description for problem number 12 in your book. Okay, or at least it relates to problem number 12. Problem number 12 talks about the 12 days of Christmas. And the traditional 12 days of Christmas are not these. So you guys know the song of the 12 days of Christmas, right? On the first day of Christmas, if you look at me, partridge in the pear tree, right? And then we increase it from there, okay? And I think they actually put the ones in there. But I found this and I thought it was really neat. This is the religious symbols. It tells you what the religious symbols are for the partridge in the pear tree analogies. So we're going to read through these because I think they're very interesting. So the 12 days of Christmas religious symbols. Number 1, the true love refers to God. Turtle doves. Number 2, turtle doves refer to the Old and the New Testament. Number 3, French hens refer to faith, hope, and love, the theological virtues. 4, the calling birds. You need to know what the descriptions are at the beginning of what's going on. The calling birds refer to the 4 Gospels, Matthew, Mark, Luke, and John. 5 golden rings refers to the Pentateuch, the first 5 books of the Old Testament. 6, the 6 geese a laying refer to the 6 days of creation. And then 7 swans of swimming refers to the 7 gifts of the Holy Spirit. 8 maids a milking refers to the 8 Beatitudes. 9 ladies dancing refers to the 9 fruits of the Holy Spirit. 10 lords a leaping refers to the 10 commandments. 11 pipers piping refers to the 11 faithful apostles. And 12 drummers drumming refers to the 12 points of doctrine in the Apostles' Creed. So you actually need to know the information at the very beginning of each of these. This is actually what they're referring to when the song was written. Pretty cool, right? I had no idea. Yeah. All right.